Thanks for the introduction. I guess everybody can hear me. So actually, the work I'm going to present, most of it actually started with a paper by Victor in 2004, which has been a great source of inspiration. And we actually met, I think, in 2008 for the first time. And since then, we have been discussing solving very hard problems. The first problem, Victor says he really... Oh, I guess you have to fill in your password. Yes.
Yes.
Nobody
was.
Oh, it's actually. Okay, so. So the first problem he really wanted me to solve is sure number 5. I remember that clearly from the 2008 workshop where we met. And although it's not in the presentation, this is a problem I finally solved a few months ago. And the proof is 2 terabytes in size. And so these are kind of the problems we can finally solve now. But what I also kind of, we recently got quite some media attention, and the cool thing I think is that we can solve problems that couldn't have been solved so far, and actually that we can verify them. And of course the verification requires a proof, and these proofs are enormous in size, and somehow people seem to appreciate the enormous size of these proofs. Although we really try to make it as small as possible, it's much easier to make a big proof, but size seems to matter, and since I used the second title, many more people kind of seem interested in the topic, so that's where the everything is bigger in Texas comes from. How many people of you know here about subsolver? Yes, okay, about half. So I just do it very briefly. There will be hardly any formulas in here in the talk. So what is satisfiability problem? So how it works? We have a problem in all kind of different domains. Most importantly, formal verification, but also for its security. Can we find hash collisions efficiently? Can we find patterns in bioinformatic instances? The first actually application was that I am aware of was for the Dutch train systems in the 1980s. It's used for planning and scheduling, and for example also in automated fair proving, which is actually first order, or to automatically make exploits. How does it work? We have all these problems in these domains. They're typically kind of a few kilobytes in size if you have them in some representation. Then we translate them to propositional logic. They frequently become gigabytes in size. Then we give them to the so-called subsolver, which can solve them typically faster than most people can actually write a parser to write these formulas. And then we have the solution, and we translate the solution back to the original domain. By the way, if there are any questions, please let me know also during the talk. I want you to understand instead of that you have to wait to the end. So I very briefly discussed some of the media attention. So Victor, I, and Oliver Kuhlman solved the problem of the Pythagorean triples, which I will talk about more later. We submitted it, got accepted. I put it on Arxiv, and a few days later I got an email from an editor from Nature that they liked the paper and that they wanted to make an article about it. So I had a 70-minute conversation with them, or with her. And what I really tried to tell her, it's actually what I'm also really going to try to tell you, is that subsolving is cool and that we can have linear time speedups even if we have thousands of cores. But if you read the article or all the media attention that came with it, you read nothing about it. There you don't see any about subsolving, it's only about the size of the proof. So for you, the cool thing with, I think, subsolving, but I hope to convince you that it's how nice it is and that you can actually have linear time speedups to solve large problems. But before I'm going to kind of convince you of that, I'm maybe discussing whether this technology is really useful, because especially if you look at the Nature article, they say it's just ticking off possibilities, we don't understand anything that's going on, and so maybe before I start to do anything, is mechanized mathematics meaningful? And of course, it's a clear yes for me, but so let me try to convince you as well before I start. This very same techniques that are solved for mathematics to automatically solve mathematical problems are used in industry for hardware and software verification. And another important thing here is that problems from Ramsey theory, I won't go too much into detail here, but they seem to be very hard, and even the small Ramsey numbers that have been solved in the 50s and 60s and 70s, if you look at those papers, they're great. So it asks about properties of graphs, and what you see is enormous case-splits of graphs, pages and pages and pages, and somehow it seems that these problems, the only way to solve them is a big case-split, and there doesn't seem to be any kind of elegant mathematics possible to solve them. And it really comes then back to the question is, what makes a problem hard? Maybe some problems you cannot have a short mathematical proof for them. Apart from solving these problems, we actually produce proofs. These proofs are checked, and these proofs contain lots of useful information. One of this information, for example, is that you can compute an unsatisfiable core, which shows which parts of the problem were required and which parts were not. And typically many problems have quite some redundancy which is not required to prove unsatisfiability, and this might also give you quite some insight in the original problem. And I think we can simply not afford to only have answers for questions that humans can deal with. And to kind of elaborate on the last point, solving may be able to produce facts, and I will show you some of these facts, and we might not understand why we can, the reasons beyond these facts, or behind these facts. For example, if we have two systems, so one system, we can show that we can completely verify it, and we know that it has certain properties like security, safety, and for the other system, we cannot prove anything. Although we might not understand anything about the proof, how we got the safety and security properties, we really want to use the system for which we can be sure that it is safe. And so, we might not be able to understand it, but our ability to compute those facts makes this technology quite meaningful. So this is the outline of the talk. So first of all, I will talk about some of the hard problems that can be tackled with this technology, and then I will briefly discuss satisfiability solving and how to achieve linear time speedups, even when using thousands of cores. Not only do we want to solve these problems, but it's only natural to doubt any computation that takes years to solve. So we want to go beyond solving, and we actually want to produce a proof, and we want to verify this proof using trusted tools. So that's what I also will talk about, and then also conclusions at the end. So first, some hard problems. So there are many hard problems in AI and formal methods and many other related topics. And if you look how things have been there, so this is kind of a very short outline of how things have been. So in the last decade, we were able to solve very hard problems in hardware verification. Companies like Intel, AMD use SAT solvers to check very big problems, and they take many, many hours to solve, if not days. And so the reason why we're able to solve them using satisfiability is because the translation from hardware to propositional logic is very natural. And this doesn't hold, for example, for software. Now, I think the next step, what we are going to see, is that we can solve hard problems coming from mathematics and especially from combinatorics. Why is this kind of a next step? Because problems in mathematics, or especially combinatorics, they can be formulated compactly, but the concepts are much more complex. And this is what we are able to see now, so we can solve problems for von der Waals numbers, Schur numbers, Euler's discrepancy problem, Pythagorean triples problem. All these problems have been opened for decades, and these days we can translate them into satisfiability or to propositional logic and solve them fully automatically. I think the next step, but that we're still quite a bit far from it, is doing software verification. Already software verification uses SAT and SMT solvers quite a bit, but if you look at the problems they can deal with, it's either you can solve them in a second, or you won't be able to solve them at all. And what we really want to see is hard problems that you actually scale and you can solve them instead of what we have seen with the other areas like hardware verification and these days mathematical problems. So I briefly discussed, for instance, what problems can be dealt with in industry. Most of the things what the industry is using is combinatorial equivalence checking. So what you want to do is you have a specification and an implementation, and you want to check whether they're functionally equivalent. How are you going to do this? You translate both of them into propositional logic, and you ask, is there an input for both of them such that the output is different? If the answer is no, then they're functionally equivalent, and otherwise you have a counterexample. And the same thing is used, for example, to optimize designs. Is you have a design before optimization, you have a design after optimization, and then you ask the same question, does there exist an input such that the output is different? For software verification, I think there's lots of interesting applications in the future. First of all, we really have many important problems in cybersecurity, and that given certain reasonable assumptions, such that nobody shares their password or other things, can we show that only authorized people have access?
And is this reasonable in what world?
Of course, without certain these kind of things, there's nothing, right? So, but I think you have, at least if you can trust the machine, that we are really so much further, right? One of the other things which is very hard is because we know that machines can do, or programs do what we tell them to do, but the important thing is that we don't want them to do anything else. How are we going to formalize this, and how are we going to check that for all possibilities this is not the case? And for example, another question is, in case of failure, if we rebooted no information, how can we want to make sure that no matter what the situation is, this kind of properties can be held. And things like autonomous transportation, the questions become much more difficult, and that is at least 20 years away, whether, for example, we can compute whether an autonomous vehicle will obey the law. How are we going to formalize these questions and then compute them? Now, in case that there's an accident, an autonomous vehicle did nothing wrong. So there might be some decision, but why did it make that decision, and how can we show that it did nothing wrong? Or in case of safety, the safety of passengers and the public is always the highest priority, and not that the vehicle gets completely destroyed. But I will focus mostly now here on mathematics, and especially the Pythagorean triples problem. So the Pythagorean triples problem dates back a century ago, when Schur started to asking questions about coloring the natural numbers. So he asked questions such as the following: will any coloring of the positive numbers with, say, two colors, let's call them red and blue, result in a monochromatic solution of the equation A plus B is C? So he asked the question for any finite number of colors in 1912, and he proved in 1917 that for any finite number of colors, the answer is yes. I will now show you that the answer is yes for two colors. So we have on the slide, there are all 6 solutions of the solutions of A plus B is C, if A, B, and C are less or equal than 5. And if we try to color the numbers 1 to 5, then 1 has to have a color. Doesn't matter if it's red or blue, so say we pick blue. So in order to avoid the monochromatic solution of this equation, because 1 and 1 is 2, 2 has to be red, otherwise we have an all blue solution.
What's wrong with an all blue solution?
That's the one that we're trying to avoid. So the question here is, will any coloring avoid a monochromatic solution? So in order to answer that question, can we avoid this indefinitely? We try to find that you're forced to pick the other color for as soon as there's only one option left. So 2 is forced to red, because 2 plus 2 is 4. We now are forced to color 4 blue. And what we see now on the top right, 1 plus 3 is 4, so 3 is forced to red. And we also have 1 plus 4 is 5, forces 5 to be red as well. And if we color them both red, then we see that the last solution, 2 plus 3 is 5, is monochromatic. So with just the numbers 1 to 5, we cannot avoid it. So any coloring of the integers, because the numbers 1 to 5 is part of the integers, we will always, the answer is yes. But not only, so people after the early 1900s have been looking also in the 50s and 60s and 70s to all kinds of other equations. And one of the equations, but I just have another equation here, just as an example, will any coloring of the positive integers with 2 colors result in a monochromatic solution of a cubed plus b cubed is c cubed? We know the answer is no, because we know from Fermat's last theorem that there are no solutions in the positive integers for this equation. So no matter how the coloring is, there's no monochromatic solution because there are no solutions. So many more equations have been studied, but one of them, and so typically what you can see is that if there are many solutions for an equation, the answer is yes, because you cannot avoid it. If there are few to no solutions, the answer is no. And there's kind of a sweet spot with the equation a squared plus b squared is c squared. There are quite some solutions, but it seems that you can avoid a monochromatic solution for a very long time, even so if you have 2 colors. And so here on the slide I have all the solutions up to a and b and c less or equal than 40. And it's very easy to make a coloring like this. For example, the coloring I made here is that every number that has an odd number of factors, 5 or 7, is blue, and all the other ones are red. And actually you can make, you can color lots of numbers with easy patterns. So the answer was kind of maybe, because you can really extend and go bigger and bigger and bigger. And Ronald Graham named this the Pythagorean triples problem. The same question, can we avoid a monochromatic solution a squared plus b squared is c squared? The best known lower bound is a coloring with red and blue from 1 to 7,664 by Cooper and Overstreet in 2015. And Myers actually conjectured that the answer is no in his PhD thesis. So he actually claimed that we could do this indefinitely. The approach we took in solving it is as follows. We translated it into propositional logic and tried to find whether it's unavoidable. How did we do it? For each number, so we picked an interval 1 to n, and for each number we created one Boolean variable. So xi, if it's assigned to true, it means that I is colored red, and if xi is false, it means I is colored blue. And for each Pythagorean triple, we have 2 clauses, one stating that either A, B, and C is red, which is the first clause, or the other clause means that either A, B, or C is colored blue. And the main result we have in our 2016 paper is the following. You can color the numbers 1 to 7,824 with 2 colors, but it is impossible for one higher or more higher. And if you have the right heuristics, this can actually be computed in, say, a minute. while the best method we have now to compute this is 40,000 hours. So, and the problem that if you look at the sub-encoding of these problems, it's only 14 clauses difference. So you add 14 clauses to the problem and it becomes from solvable in a minute to 40,000 hours. And that's after lots of optimizations to actually get it solved efficiently, right? This is, for example, one of the solutions, or actually many of the solutions, of 1 to 7,824. If you want to look at the physical copy, it's in Victor's office. What does it look like? What is shown here? I talked about coloring things with red and blue, so why is there so much white in this image? White means that a number can be colored either red or blue. So actually this doesn't show one solution, but 2 to the power the number of white sub-solutions. So what you see here is, yeah, it's not very clear, but this is, so the lower left corner is the number 1, and then next to it is 2, 3, and if you go one row up, it's plus 100. So this shows all the numbers 1 to 7,825. And this also kind of shows you the reason why it's relatively easy to compute a solution, because there's not one solution, there are many, many, many solutions. And actually, I have been trying to count all the number of solutions for this problem, but this is still an open question. How many solutions are there for coloring 1 to 7,824 without a monochromatic solution? Now, the methods. So, sub-solving and how to achieve linear type speedos. So, the short story here is that there has been quite some progress since the early work of Davis and Putnam in the early 60s, but so the result in, say, mid-90s was that we could solve formulas from various applications with thousands of variables and thousands of clauses. And these days we can solve problems from industry that have millions of variables and millions of clauses. So there's this enormous progress in solving things efficiently. If you want to know more, there is this handbook of satisfiability, in which Edmund Clark calls it a key technology of the 21st century. But also there is, since a year, there's also a book by Donald Knuth on satisfiability solving. It's actually a subsection of the art of computer programming, so it's section 7.2.2.2, but it's 316 pages, so it's by far the biggest subsection of the art of computer programming, and there's lots of cool stuff in there. So if you want to know more, check out these two books. There are two main complete subsolver paradigms. The first of all, and it's the most famous one, is CDCL. I have been giving tutorials of 2 or 3 hours about just CDCL, and you have to do it just with these lines. So what is CDCL? How does it work? So CDCL, so you have this big formula, and what it tries to do is it picks a variable almost at random, assigns it to a variable, picks another value, assigns it to a value, and it continues to do this until one of the clauses becomes falsified. So it has all the clauses assigned to false. Then the reasoning starts to kick in. It translates this conflict into a new clause, which is added to the formula, and then you practically start over again. And this is continued until either you hit a solution, which is, or the other case, which it actually tries to do, is to find a short refutation. So CDCL is a method by assign, conflict, add a clause to the formula, start over and do this until either you learn the empty clause or you hit a counterexample, which is the solution. This is very effective on large, easy formulas, but it has also a big problem, which is that it's very hard to parallelize. The alternative is called look-ahead, and what look-ahead tries to do is you start with a formula, and now you pick a variable, and you assign it to true and to false to have two other formulas. And then you recursively start doing this again. And by picking the right variable, you hope to try to get a small binary search tree. This method is quite effective on very hard formulas, but because it's very expensive to pick the right variable, this is also very costly on these large, easy formulas. And there's another thing, and actually that's also, I will elaborate a bit on the next slide. If you look at a lot of the progress in the last 10 years, it is actually based on re-encoding. So what you see, the strongest solver, for example, Ling-a-Ling, it is CDCL based, but what it does is second it tries to re-encode it using all kind of rewriting rules and other tricks, and then it applies a second CDCL to find a short refutation. And then it switches back to kind of re-encoding and simplification, and then search. So there's a constant interleaving between search and simplification or re-encoding, and adding more and more of these kind of re-encoding techniques is crucial to actually solve things efficiently these days. To give you an example of such a re-encoding techniques, one of them is called sub sweeping. How does it work? So, for example, we have the problems I told you earlier from combinatorial equivalence checking. You want to check whether specification and implementation are equivalent. But how you do it, you ask if there's an input such that the output is different. Frequently, when you have such a problem, many of the variables in these formulas, from the specification and from the implementation, are actually equivalent. So you actually want to find out early that they're equivalent, such you can substitute one by the other and thereby simplify the formula. How are you doing it? So you take out the constraint that they have to be different, you randomly give assignments, and then you get assignments to all the variables in the circuit, and you do this frequently and you find patterns. Is it always the case that this variable is equivalent to that variable, or this variable always the opposite of that variable? If that's the case, then you actually, or when you find these patterns, you assert them in the problem, solve it. If it's and if you find that it's actually always holds, you simplify the problem. And you do this until you have none of these pairs anymore, and then actually you start solving the problem with all the other techniques. So there are all kinds of techniques and this you can do for circuits, but you can actually use the same techniques for many other problems. Now about how do we parallelize this? So the most used techniques to parallelize sub-solving is as follows. We have a problem and we have a CDCL solver, and we use multiple CDCL solvers with different configurations, and we just give the same problem to the solvers, and the only thing what we kind of have to do is we're going to share some useful information. So if they're able to learn short clauses, we're going to share it. And the first solver that solves the problem kind of wins, and then you're done. This kind of works nice for for those large easy problems, and if you have, say, 16 cores, but this really doesn't scale if you have a big cluster, because first of all, it is definitely not linear scaling with this technique, and also the bigger you go, there more communication is required, and it slows everything down. And what you actually have seen, for instance, in the competition is that for some solvers, if the implementation is not right, you run it with 48 cores, and you run it with one core, and actually the implementation or the execution with one core is faster than with 48 cores, because it is the communication and the memory problems slow things too much down. So the alternative is a method that I worked on with several colleagues. Is called cube and conquer. what does cube and conquer? It tries to combine both of the main paradigms, so CDCL and local, and then look ahead. How does it work? So we start with look ahead, and we build this binary search tree. But at some point, we say, okay, at this point, I expect that CDCL will be faster in solving this problem, and then we give it to a CDCL solver. So the main philosophy behind this is that CDCL is very good at finding short refutation, but only if it exists. And many of these hard problems, they don't have a short refutation. So what you want to do is you want to split the formula into many pieces until a short refutation arises. Then at that point, typically look ahead is no longer good enough, and you want to switch to CDCL and solve that subproblem using CDCL and continue. So what's actually happening is you have a formula F, and then you split it into n subformulas. And each of these subformulas is then solved using CDCL. The difference with portfolio also is that there is zero communication. Because these subproblems should be independent. If the splitting is correct, it doesn't make any sense to do sharing. You have a question?
Yeah. My experience with this is that the subproblems are extremely variable with respect to how hard they are. And therefore, some of them will be solved very quickly, and some will take forever. So it's quite difficult to get. You say near equal splitting. I'm wondering how you do that.
That's on the next slide.
Okay.
So let me go answer your question by switching to the slide. So many people tried a similar approach in the past. So they have a machine of say 32 cores, and they split the problem into 32 problems, and then the total runtime is say 80% of what it was, because there are few problems that are almost 80% of the original problem. That's exactly what and some other problems are just 1% or even less than 1%. This is also what you see on many problems, and why this approach was discarded by many people. But they didn't try. So this is the following is the key to actually solve things efficiently. So we now consider the number of problems that you can solve. So one is if you split nothing and then you have pure CDCL, and if you go almost to infinity, say to infinity, you have pure look ahead. And now we're going to see what happens if you start to increase n by steps of a factor 10. So here we have a problem. It's the subproblem from sure number 5. And if you run it with pure CDCL, then you can solve it in about 1,000 seconds. And this plot, actually, all the runtimes are on a single core, so there's no parallelization at all. And what happens if you split it into 10 subproblems? What you see is it goes up to over 2,500 seconds. So some of the subproblems are as hard as the original problem. And the interesting thing is, as soon as you split it into 100 subproblems, the total runtime actually goes down back to 1,000 seconds. And the interesting thing is, if you split it into 1,000 subproblems, it goes down, and at this point, the purple shows you the cost of splitting. So at some point, the splitting cost becomes so high that it doesn't pay off anymore. And what you see here is that, say, with 150 seconds, you can solve the same problem if you split it into 10,000 subproblems, and this includes the cost of splitting. And again, this is just solving everything on a single core. If you solve these problems, say, with 10,000 cores, it's less than a second. So,
when you're solving those 10,000 problems, are you stopping as soon as any one of them reaches a solution, or you have to do all